In this series of videos, we are going to continue talking about direct proofs, but we're now going to talk about direct proofs that have a little bit less of a rigorous structure than the ones that we've been talking about in the past. So first, I'd kind of like to motivate why we're going to be deviating from this structure that we've provided. The structure that we have so far, which is to always make sure you're stating your assumptions, then state next what you're going to show, then write down important definitions, and so on and so forth. It's a really good outline, and it's a good way to gauge whether or not you're being perfectly clear when writing a direct proof. But here is the train of thought behind this. So first of all, clarity should always be the gold standard for your mathematical writing. This point is made very clear in the book of proof, and I really do believe that this is the number one thing that you should keep in mind when you're working on writing a proof. You want to be clear, you want to be convincing, you want to help other people understand what you're trying to show. Given that, there really is no prescription for clarity. What's clear to one person might not be clear to somebody else. What's obvious to one person might not be obvious to somebody else. There really is no way to be 100% certain that the things that you're saying are perfectly clear. And it's going to follow from this that there are times that there's no way to just write down if you show A, B, and C, then everything will be perfectly clear. There are going to be times where following the standard format of a direct proof is not really the best method. It might sort of belabor the point and make it less accessible than it really should be. Now, as long as one keeps in mind the definition of a proof, that it's a formal piece of writing that covers all cases convincingly, and as long as you're keeping clarity in mind as your gold standard, then one can really write proofs without using our rigorous template. I enjoy using this rigorous template, particularly when you're first learning to write proofs, but every now and again it's going to be necessary to sway from that. Whenever you're writing any kind of direct proof, using the template that we've been discussing in class or not, I think that there's a good checklist for a handful of very important things we can go through to make sure that we've really written a good start to a proof. The first thing is the writing and the methodology of your proof clear? If you're going to deviate from the norm, have you explained that you're going to deviate from the norm? Have you explained what it is you're trying to show? Have you always been writing in full sentences and trying to break things down into understandable pieces, etc.? Second, if you have an assumption, have you stated this assumption clearly somewhere in the proof? Anything that you're assuming, you need to tell the reader that you are assuming. If you're using any theorems that they may be unfamiliar with, these should be referenced. They should be provided if necessary. Theorems, definitions, assumptions should all be stated and easily accessible. Are all of your lines of reasoning validated? If you say, it follows that blah, then you should really say why that follows. So if you think that it's clear, if it's very elementary, that's okay, such as, I think at this point we'd say an even number plus an even number is even, then you may not need to say this depending on the maturity of your assumed reader. But at any point in time that you're making an argument and trying to justify a piece of work, you really ought to be able to thoroughly justify it, either easily if someone asks, or by pointing to one of your assumptions, definitions, or theorems. And last but not least, are all cases covered thoroughly? If there is any particular situation, it really ought to be brought up. If it's possible that something could happen, you need to at least mention what's going on in that situation. If you can do these four things for any type of proof that you're writing, then you really should be on the right track for having a good, solid proof. Now, as an example, I'd like to talk about one of the times that it really is beneficial to deviate from this template of a proof that we have, and that's when working with existence proofs. So, for example, if you're asked to show that there exists X such that statement P of X is true, this would be what's called an existence proof. All you're trying to show is that P of X is some sort of mathematical statement, and sometimes, at least once, it's true. The easiest way to accomplish this is to just show it. Here's an example of where it works, and verify it, and at that point you've rigorously proven that there exists at least one time that this statement is true, because you've given the one time. Now, somewhat similar to this is you could be asked to show that a universally quantified statement for all x, q of x, is false. So let me explain that a little bit further. Suppose somebody comes up to you and says, "It is always true that blah holds." And perhaps you disagree. Perhaps you do not think that it is always true that blah holds. Then what you're really doing is you're negating their statement. You're saying it is not true that this always holds. And the negation of a universal quantifier is an existential quantifier. So in showing that a universally quantified statement is false, this turns into a case where you're trying to show that an existentially quantified statement is true, where that existentially quantified statement is a negation of the statement they gave you. When we do this, it secretly is an existence proof, but we sometimes call this providing a counterexample to something. And all we have to do in that situation is demonstrate a single time where the statement q of x, the statement they're asserting is always true, is false. Now, as an example, I'll give an example of an existence proof and why we'll go through why we're not going to follow the precise template we've described before. But suppose we want to show that there exists a positive integer that can be written as a sum of cubes in two different ways. Now, cubes, what we mean by cubes is cube of an integer, or cube of a positive integer for that matter. So show that there exists a positive integer that can be written as a sum of cubes of other positive integers in two different ways. Now, all we really need to do to prove this rigorously is exhibit such an integer that can be written as this sum in two different ways. And it just so turns out that the smallest magical number, if you restrict your attention to positive, writing positive integers as a sum of positive integers, cubes of positive integers, then the smallest magical number with this property is 1,729. And let's demonstrate that we can write it as a sum of cubes in two different ways. We can write it as 1 cubed plus 12 cubed, just 1 plus 1728. Or we could write it as a sum of a different collection of cubes, 10 cubed plus 9 cubed, which is 1,000 plus 729. Now, there's a really funny mathematical story about this particular example. There's a mathematician, somewhat modern, named Ramanujan, who was just absolutely brilliant. And his life story is absolutely fascinating, and so fascinating that Hollywood decided that they were going to document it in this film, The Man Who Knew Infinity, which was recently released, 2015. I haven't seen it, but it looks really interesting. And Ramanujan grew ill at one point in time and was in the hospital, and he was extremely depressed. And his mathematician friend, Hardy, decided to go visit him in the hospital and was trying to come up with ways to cheer up Ramanujan. And so Hardy realized on his way to the hospital that he was in cab number 1729, and he walked in to see Ramanujan, and he was going to tell him about his cab number. He thought the number was interesting for this particular reason. And when he walked into the room, he said, "I rode over here in cab number 1729, and Ramanujan said, 'Oh yes, that number is very interesting. It can be written as the sum of cubes in two different ways, and it's the smallest such number.'" So even when Ramanujan was practically on his deathbed, he's just laying around, and he immediately saw what was interesting about the number 1729. He's an absolutely fascinating mathematician. Now, I want to give you a little bit of a warning about examples. So when you're doing a proof of an existential statement, or if you're providing a counterexample to a universally quantified statement, a single example is enough to thoroughly complete that type of a proof. However, if you're not in these very specific situations, no amount of examples is sufficient to constitute a proof. So a lot of times I'll see people trying to do a proof, such as suppose that a number is even if and only if its last digit is one of 0, 2, 4, 6, or 8. And so a lot of people will just start listing out even numbers, and they'll say, and so on, this pattern continues. And I'd say, that's not actually a proof. You've given me a bunch of examples, but how do I know that after 100 of your examples, the whole situation doesn't just fall apart? And sometimes people think you're being kind of ridiculous when you say that as a professor. So I'd like to give you this example, just warning you that examples can be helpful, but no amount of examples is going to constitute a proof. That's what we really need proof for. We need to take something totally arbitrary and prove that it's always, always, always true. Another great mathematician who figured something out along these lines was Euler, a phenomenal mathematician, and he gave this formula, f of n, which is n squared minus n plus 41. And he said, this is a function that seems to be a prime number generator. That is, if you start plugging in values for n is 1, 2, 3, 4, 5, etc., you start getting the numbers. Okay, n is 0, 1, 2, 3, 4, 5, 6, etc. 41, 43, 47, 53, 61, 71. So you're not getting all of the primes, but every time you plug in a number, 0 up through 10, I think I have listed here, you're getting a prime number. And in fact, if you continue on examining the function f of n, plugging in numbers, you can go up to the first 40 numbers, and you're going to get a prime number. So if you listed out 40 examples with this function, every single time you'd be getting a prime, and you'd start to think, all right, it's true. Proof. When I use this formula, f of n, and I plug in a number n, I'm always going to get a prime number, because I have 40 examples giving me evidence to support that. Well, on the 41st example, things are going to fail. And maybe you saw that from looking at f of n or not. But suppose that I plug 41 into the function f. Then it's definitely not true that I get a prime number. Here I would have 41 squared, and then I would subtract off 41 and just add it in again. So these two things will cancel out, and what I'm left with is 41 squared, which is very clearly not prime. It's got 41 as a factor twice. So examples can be misleading, and this is the reason that professors are going to harp on you if you just list the first 5, 10 examples and say, look, the pattern continues. And it's not always the case, and that can be a dangerous line of reasoning. And although it's evidence, it's not proof. Very nicely exhibited with this example by Euler.